Let's suppose that we have a geometric distribution. So in other words, we have a variable that satisfies the criteria for a geometric probability distribution. And the probability of a success, so in other words, P is 0.2. We remember that the formula for finding probabilities associated with a geometric distribution is found this way. The probability of a failure raised to 1 less than the number of trials times P. So the probability that X is 4 is going to be 1 minus 0.2 for Q, the complement of P. So 0.8. If the probability of a success is 0.2, then the probability of a failure must be 0.8. Raised to the K minus 1. So if K is 4 this time, so that'll be 4 minus 1, and then times P, so 0.2. So we have 0.8 cubed times 0.2. And that probability is 0.1024. Let's find the probability that X is equal to 3, X is equal to 2, and X is equal to 1. So we'd have 0.8 raised to the 3 minus 1, or 2, times 0.2. And that probability will be 0.128. The probability that X is 2 will be 0.8 raised to the 2 minus 1, or 1, times 0.2, which will be 0.16. And the probability that X is equal to 1, we could go ahead and execute this formula here, but we realize that that's really just the probability of a success. But this will be K is 1 minus 1, and then times 0.2. But really what this is 0.8 to the 0 times 0.2, and anything we raise to the 0 power is 1. So we have 1 times 0.2, or just 0.2, the probability of a success. Now, let's look at something here. Let's suppose that we're to find the probability that X is less than or equal to 4. Now, less than or equal to 4 would mean 1 or 2 or 3 or 4, and we realize that we're saying or every time. And there might be some value here in listing out these values of the random variable and then their associated probabilities. So in other words, writing out this distribution, this probability distribution. X could take on 1, 2, 3, 4, 5, 6, and actually there's no end to that. It could keep going on and on and on like this forever. So the probability that X is 1 is 0.2. The probability that X is 2 is 0.16. The probability that X is 3 is 0.128. The probability that X is 4 is 0.1024. And then we have some probabilities that are going to continue on here forever, and we haven't calculated those yet. But we're supposed to find the probability that X is less than or equal to 4. Again, that means 1 or 2 or 3 or 4, and these would be mutually exclusive events because they cannot occur at the same time. So that means that all we'd have to do is add each of these probabilities without having to worry about subtracting any overlapping events. So we'd have 0.2 plus 0.16 plus 0.128 plus 0.1024. And that's going to give us 0.5904. Now a question comes up, what is the probability that X is greater than 4? Now in this case, that would be the same probability as the probability that X is greater than or equal to 5. Strictly greater than 4 would be anything from here forward. So in other words, since this is a discrete probability distribution and there isn't any value for x between 4 and 5, then this would just be the probability that x is greater than or equal to 5. Another way we might say this is at least 5. Well, there would be infinitely many things for me to add up here if I did this by just adding. But the thing that we have to remember is that for any probability distribution, the sum of all of the probabilities has to be 1. So really, all I'd have to do to find the probability that x is greater than or equal to 5 is subtract from 1 the probability that x is less than or equal to 4. Subtract all of this off, and I'm left with all of this. Actually, what I was looking for. So that's going to be 1 minus 0.5904, which is going to be 0.4096.